Hello. Today I'll be speaking about open source video processing pipelines. This is a very large topic and I only have 15 minutes, so you can read more if you go to www.pythonlinks.info. We're all familiar with the DJI drones, and it turns out they actually have open source SDKs, multiple SDKs with MIT licenses. That's great, good step in the right direction, but the hardware, you don't get the design files for the hardware, you can't manufacture it for yourself. On the other hand, there are things like the RunCam Wi-Fi Link version 2, which are completely open source. What this does is it takes a HDMI or DVI cable from a camera, and then it broadcasts the information over Wi-Fi with very low latency. And so the case is open source, the circuit board is open source, the software is open source, the whole thing is open source, well, except for the chips inside. And so that's really good. You can make it yourself, you can change whatever you need to. My expertise is actually in the cameras, so let's talk more about the cameras, the open source camera stacks. So in the old days, we used to think of a camera as something on the left-hand side with a case and a button. Nowadays, we think of cameras more like what's on a cell phone. They can have multiple image sensors with different focal lengths, with different times of exposures. They even have range sensors, and all of that's integrated together in real time at 60 frames per second. Very impressive. But when engineers talk about cameras, they're really thinking about something more like the Raspberry Pi. It's got a sensor, it's got a lens, it's got some cables, it's got some electronics. And what you can do with these is you can plug them into the Raspberry Pi Zeros. The Zero is only $10. The Zero 2W is $15. It gives you 4 cores instead of 1. It's got a DVI output, USB 2, DPI interface. There's LibCamera, which controls the camera. So very large software stack there. There's a lot of useful stuff. And RPI cam apps that actually display it and so forth. So amazing amount of functionality for very little money, very small size. And then there are a lot of cameras that plug into this Raspberry Pi ecosystem. Here we have the WaveShare OV5640. It comes with a fisheye lens, good for drones, $16 to purchase it. If you get the rectilinear lens, well, they generally need autofocus, so that's heavier and larger and requires more money, like $26 with flash. You can see there the 19 pins for 14-bit data, or here you have the white is a 38 FPC connector, which will give you 24-bit data. These cameras have a lens. You may have studied this in high school or college. Of course, now lenses are much more complex. This is a lens design from an iPhone patent in 2016. There are a lot of these image sensors, 874 in one database, and they actually don't list a number of the camera vendors I listed at the bottom. And so all of this stuff gets assembled into these camera stacks. Here we have the Arducam USB shield. At the top level, you can see the camera, the lens, and the sensor on the top board. On the bottom board is a USB connector, either USB 2 at 480 megahertz or USB 3. And in the middle, you have adapter boards. So they have 2 of these USB boards at the bottom, a bunch of camera adapter boards, and a huge number of cameras on the top board. You can assemble them. Here's another camera stack from ReCamera. Very nice metal case. You have to have the metal case because the microcontroller in the middle of this particular camera stack gets very hot. What do you do with these camera stacks? Well, there are a bunch of processes you can do. Here's video cropping. So it's really easy to crop a static image, but if you're doing this on a video at 60 frames per second, it's more complex because for every second you have to release the next image, and also the crop size may be different than the display size, so you have to scale it to fit. Doable. Another thing they do is defective pixel corrections. So if you have a short circuit, then on a black background you'll see a bunch of white dots. And if you have an open circuit, then on a white background you'll see a bunch of black dots. So both of those need to be corrected by averaging with adjacent circuits. You can do pixel binning. So the basic way sensor works is you have many different cells on the sensor, each with a different color. And if you have a very low resolution, like a Wi-Fi connection, then and a very high resolution camera, what you can do is you can bin the adjacent pixels in order to reduce your noise, get a bit better image. In the upper right hand side, we can actually see how these image sensors work. So there's an image sensor in back, and then they put a bunch of filters in front. And so the human eye is more sensitive to green than to red or blue, so we have twice as many of those. And there's a whole complex process for taking those individual cells and converting them into RGB 24-bit values. You can read that on Wikipedia. We also have to deal with camera spectral responses. This is the response to RGB on some camera. And there's also displays have a certain spectral response, and also the human eye has a response. So if you look at this woman's face on the left-hand side, clearly the color is off. So you have to adjust the colors to match the spectral response of the eyes, and they've done the color balance on the right-hand side. It looks normal. We're very sensitive to strange colors of people's skin because for health reasons we want to stay away from those who are sick, for evolutionary reasons. But the trees, if they're this color or that color, we don't really care. Here's a more computationally intensive fisheye dewarping. On the upper left-hand side, you can see the fisheye. The rest is the dewarped image. If you have drones fighting each other and trying to recognize each other, it's very hard for AI to recognize distorted images. And so AI drone warfare definitely needs dewarping. Another stage in the pipeline, at some point you're going to get this, you may get this HDMI signal and you want to bring it into a USB, so they have these $10 USB dongles, less than $10. Make sure you get the USB 3, not the USB 2 dongles. And basically how this part of the image processing pipeline works is you have a double frame buffer. So the HDMI data comes in for one frame, you write to one frame buffer. Meanwhile, the USB is reading from the other frame buffer. And then they swap, and the USB reads from the one which was just written, while the HDMI writes to the other one, and then they swap back again. So that's really hard for microcontrollers. Microcontrollers have a really hard time with even processing high bandwidth video. They're just not fast enough. And you add a frame buffer, there's no memory left. And so there's a really cool library called libmpix, which runs on Zephyr OS. And what that does is it does a ring buffer. So when a pixel of data comes in, it gets written at the one end of the ring buffer. When a pixel of data comes out, it gets read from the other end. And in between those two events, you have enough clock cycles to do some processing on the data in the ring buffer. And particularly once they get single instruction, multiple data, vector processing working, this will be really interesting. So a bunch of processes that they already support. If you actually read the paper on the website, there are at least 24 vision processes that are described there. It's a big field. And so these microcontrollers, they have difficulty keeping up with large video bandwidth. Really what you need are these devices called FPGAs. What's an FPGA? Well, simple story is it's a very parallel circuit which is really good at processing videos. What my interest is the open source ones. And so when we say open source FPGAs, we don't mean that the circuit design is open source, we mean that the software tooling is open source. So you write some Verilog, Yosis converts that into a circuit diagram, NextPNR then places that on the FPGA, and there are a bunch of these tools that support it. The one that gets the most notice should be Lattice. The Lattice NX17 and 40, 33 and 40, they all have MIPI blocks for processing camera data, so they'll do 2.5 gigabits per second. So simplifies your life dramatically. Of course, since they're in this open source group, they've cornered the market on this. A bit expensive. But so on the right hand side, you can see the tinyvision.ai development kit, 217 euros plus import taxes if you're in Europe. Very nice solution, though. If you're in the European military or you're concerned about supply chains, you should go ahead and use the Cologne Chips GateMate. Evaluation board comes in at 209 euros, maybe at 15 euros for Raspberry Pi bridge there. And of course, next year in January, we're going to be seeing the $79 Ice Pi Zero. It's got the same form factor as those Raspberry Pi Zeros. You just click them together, and it's got everything you need. Another interesting open source video pipeline are the frame glasses. They have a camera, they have an FPGA, they have a display on the frame. And so you can see on the right hand side, on the big white square, there's a Bluetooth a microcontroller that speaks Bluetooth to the rest of the world. There's an FPGA. Below it, you've got a camera sending signals in. Above it, there's a display. So the basic way it works is you've got the image comes in from the camera. It goes from the SPI driver to the microcontroller. It gets sent off to some AI which recognizes the image, and then that goes back to the graphics. The results go back to the graphics pipeline to be displayed. I'm going to skip the graphics pipeline, focus more on the camera pipeline. So you start off with the camera. It transfers the bytes over MIPI D-Phi. So you create pixels, and then you have to do this whole debayering process. Then we crop it because you probably don't want the whole image. You can compress it with JPEG encoder, store it to your frame buffer, and then send it off over SPI to your microcontroller, and from there it goes to the cloud to do the AI recognition. So on all of these image pipelines, the last step is often going to be some kind of display. It's evolved a lot from VGA to DVI, HDMI. Now we've got USB-C, DisplayPort, Thunderbolt, lots of different options. Every single stage of these open video processing pipelines have lots of different options. What can we do with all of this? Well, let's take a look at the DJI multispectral camera. At the top, you can see that there are red, green, and blue, and the infrareds. They're kind of a general purpose camera, but they're specifically used for measuring photosynthesis in agriculture. Actually, the amount that the farmers get paid is based on how much photosynthesis their plants are producing. So here we can see the photosynthesis spectrum, but here you can see what the peak frequencies that the DJI cameras measure. Maybe not the best for measuring photosynthesis. If we had a camera that was actually aligned where the different frequencies were focused on the peaks and valleys of the photosynthesis, we could probably get much better data out of it. And so if you try to do this on a microcontroller, well, they have a difficult time with a single camera. Imagine trying to do 4 cameras, no chance. But FPGAs can generally handle this type of work very nicely, integrating the signals and then saving them out to some file. Climate change is bad. It's getting worse. Food prices are already going up. 80% of the people in Africa are hungry. Whatever we can do to help farmers produce more food, very important work to be doing. So, what's the conclusion? This stuff is complex. If you find a shrink wrap solution that does what you need, by all means, please use it. If you need to do something custom and the bandwidth is low, try libmpix on Zephyr OS on a microcontroller. If you do need to go to FPGAs for higher bandwidth, the obvious choice is the Lattice NX 173340 with MIPI CSI and display serial interfaces within the open source community. If you're, say, in the European military, you're concerned about supply chains, then you definitely want to go with the European-made GateMate. And for all of these cameras, if they don't have MIPI, then you can use the Raspberry Pi MIPI CSI to digital video protocol to any FPGA. There's a whole nother discussion about what you do if you want to transmit the signal over longer cables. That's all covered in the paper. If you go to www.pythonlinks.info, you can reach me, Lozinski, at pythonlinks.info, or I'm also on mastodon.social, pythonlinks at mastodon.social. Thank you very much.